really simple. I mean, I don't know if you read through it all. It's chromatography, people. It's just chromatography. So this inquiry lab is super, super easy. And in class on Wednesday, tomorrow, it will probably take us 30 minutes, like 45 max, right? So you'll have a bit more time to do your analysis in class than normal. But I had to offer the flow of the week. So today I have colligative properties for practice. Tomorrow the lab, and then Jordan and Daniel, I'll see after or at the end to talk about what I'm doing for you there. FRQs we're dispersing and sprinkling throughout, okay? And then the Thursday right here says Spectra Day, so we're gonna recap mass spectroscopy, and then like IV, IR, UV, something else spectroscopy, chromatography. We're gonna talk about a lot of spec stuff. And then it's pretty much, I'm going to give you guys some stuff. You're going to make a quick 5-minute presentation. We're going to present in class. It's really easy. It's really actually got some really cool information with it. So that'll be really fast. And FRQs. And then the last day we're finishing up with environmental chemistry, because there's a lot of solution chemistry and environmental chemistry. So we kind of need to pull that cross-curricular nature of this class together. And we'll do some multiple choice class. So I did that because I hear people are going to be out Friday. So you just have to watch the video and do the multiple choice by yourself. Okay, so I just had to, I need you here Thursday. I need that from you, okay? And tomorrow. But, band. Okay, so we're going to talk about colligative properties first. So keep your day 2 stuff on your desk. And your down later, we'll finish that after this. And I understand the Java, you never fear. Java is fine, okay? Java will not kill your computer. Your computers will go, oh no, not Java. It's lying. It's fine. It's fine to download. If something happens, I'll have my husband fix it. He's good with computers. Okay. So here are your 2 equations for the second and then third type of colligative property. Yesterday we talked about vapor pressure, Raoult's law. We did mole fraction times the pure solvent pressure equals partial pressure. So that's vapor pressure stuff's all related to this. So write down what you need to. It's on the sheet. Okay, so with our vapor pressure, we talked about how the non-volatile solutes will cause a decrease in vapor pressure simply because the non-volatile solutes don't cause vapors because they're not volatile, they're not evaporating. So basically, if you don't have 100% of solvent at the surface, it's not going to vaporize as much. Just basically, the vapor pressure is lowering. So this is really similar. Because what's the definition of boiling? Avery and I have done it 3 times now. Vapor pressure. Right, so like the atmospheric pressure, right? So I'm going to say when vapor pressure equals atmospheric pressure, because after that point it starts to boil, but once it hits that point, essentially it's starting to boil, right? So if we've lowered the vapor pressure, that means that as you lower the vapor pressure, the atmospheric pressure is winning over and over and over again. So what do you have to do to that solvent to crank it up so it starts to vaporize at that pressure? Huh? I'm assuming, so this is like vapor pressure equals atmosphere, that's for normal solvent. If I add the solute, the non-volatile solute, I've effectively decreased the vapor pressure of the solvent, of the solution, right? Solution. So I've decreased the vapor pressure of the solution, and I want the vapor pressure to equal the atmospheric pressure. I'm going to have to crank up something. What? Temperature. I've got to increase the temperature of the solution to make it vaporize at the point where vapor pressure equals atmospheric pressure. That means I have to raise, essentially I'm raising, bless you and stuff, raise the boiling point, okay? I never know to say for coughs. It's not bless you. Okay, so we need to increase the temperature, which therefore to increase the boiling point. How much does it increase? It depends on the molality. Units for molality. Moles of solute over solvent. And most of the time, solvent is water, but it does differ based on non-polar solvents, polar solvents, stuff like that. So we will have different solvents, so be aware. So this is actually there we go. Okay, so we were saying before the fire drill, a modified version of this is Little k is a constant called this one is boiling point, Malau, no, yeah, Malau constant. I think I put the opposite way. Malau boiling point constant. But basically it's related to molality. The units for little k is degree C per Malau. So you'll notice that the molality constant, unit will cancel out, leaving with degree C, which is what temperature is. Yeah.
It's really bothering me, and I really just fix it. The molau, it looks like molar.
Molau, it's because I wrote molar.
I know, it just
okay. So the modified version of this is Kim. And the reason I started doing this is because I replaced a teacher. Her name was Kim, and all the students hated her. And then I started to use this, and then I was like, "Guys, you will remember this. Your favorite teacher ever." They're like, "Yeah." So I replaced the teacher when her name was Kim. So anyway, the Malau freezing point or boiling point constant times I, which is Van 't Hoff factor, going to see that on the next slide here, times molality. Van 't Hoff factor is what we were doing yesterday. We were like, "Oh, how many ions does aluminum chloride break into?" 4. Glucose. 1. So it's just basically ionic versus covalent, okay? So freezing points can be very similar, except we're talking about boiling point elevation. Don't know if you got that. Boiling point elevation, because like I said, you had to increase the temperature at which this thing would vaporize to the point where it equaled the atmospheric pressure. This one is going to lower the freezing point. So basically, vapor pressure is used the entire time, because between solid and liquid is when freezing occurs, right? Technically, the vapor pressure of the solid, even though solids don't vaporize, they do just right? The vapor pressure of the solid equals the vapor pressure of the liquid, right? Well, if you lower the vapor pressure, you're lowering the vapor pressure of each of these in the solution form, of course, so the solution form. Therefore, you lower the point at which the vapor pressure is equal, therefore you lower the freezing point, right? A lot of dots get connected here. But there's another way to explain this, and I basically say the solutes play with the solvents and don't make them freeze, right? They just get in the way and they stop them from freezing together. So if the solute interacts with the solvent via like IMFs and stuff like that, they interact to the point where they're limiting the phase change process. So there, you can say they get between the solvent particles to limit freezing, etc. So this is the same thing. It's just delta T is equal to Kim. And I like to use Kim because it's just one fits all. You know, you just have to figure out what I is. Now the K I was talking about earlier, the Malau freezing point constant or boiling point constant, is based on the solvent, right? So you have to make sure you use a chart. You do not have to memorize these and nothing crazy. Get a chart with the different values. The ones that we see the most are KBP, water, 0.52. KFP for water is 1.86. What are the units for this again? Degree C per Malau, right? And then another one we'll see a lot is benzene, 2.53 and 5.12. So we'll see those a lot, but I'll bring this back up when we need it, okay? All right, so this is we'll do a couple problems with this. Read through this Van 't Hoff factor thing I talked about yesterday. I just want to make sure you remember. It's unitless. Key fact. He's going to keep doing it now because you told him to stop. Okay, so degree of dissociation. Basically, ionics are always going to have more than one. Covalents are always going to have a 1. The only thing that we have to be aware of is the ion pairing. Ion pairing just literally means the ions pair back together after they've dissociated. So the extent at which you think, calculated-wise, the delta T is going to change, it might change a wee bit less, just because the ions are actually coming back together as 1, so the I factor is lower than we think it is. So ion pairing for sodium, the I factor for sodium chloride is theoretically 2, but truly it's actually a 1.8 because of the ion pairing phenomena. Good? Okay. I just like to make sure you're taken care of. You just gotta let me know. Okay, so let's do this one. The one thing I do want to say for the application of this, we've done a lot of labs this year. Okay, we've done a lot of labs with dealing with molar mass specifically. You can find molar mass of a substance in like a gas way, in a titration way, an acid-base reactions way, in colligative properties ways. So you've got to have the power to use any kind of information to find molar mass. That is one of the biggest things we talk about. Find molar mass of this via a lab, an experiment. So this is one way that's a valuable application of that. Okay. So the freezing point. What are the freezing points and boiling points of a solution prepared by dissolving 651 grams of ethylene glycol, which is what you put in your what? Anybody?
Your coffee.
No, my gosh, it's antifreeze. No, it's antifreeze. You put it in your radiator. Okay, ethylene glycol you put in your radiator. Please don't put it in your coffee. Then it will never freeze. The boiling point will also be heightened. Okay. And 2505 grams of water. Okay, solvent, solute. Who's solute? Ethylene glycol. Right, okay. So finding the delta T of Kim. Let's do the Malal freezing point. What's the solvent we're pertaining this to? Water, okay, so the K, let's do boiling point first, okay? So kBp for water was 0.52 degrees C per molal. What do you think I is based on the structure? 1, it's all covalent, it's non-volatile, so we're going to call I 1. Molality, don't know yet. Got to take this lovely information and get molality. So molality is moles of ethylene glycol, so I'm going to kind of do this as one big, humongous fraction. 651 grams of ethylene glycol. I'm just going to put F there. Its molar mass is math 62. Makes sense? Yeah, okay, I'll go with that. Times 1 mole of ethylene glycol over 62 grams per mole. So that top is going to be my moles of ethylene glycol, yeah, divided by my what of solvent? Kilograms. So just bump that over. 2.505 kilograms of water. So that's going to give me molality, yeah? Molality is 4.1916 molal. Okay, so this then gives us a delta T of 2.15 degrees C. So this is the freezing point change, depression or increase. Depression. Okay. So what's the boiling point of water normal? Lied. I just did, no, I lied to you. I just wrote down the wrong number. I thought we were doing freezing point. We're doing boiling point. Boiling point. No, yeah, boiling point. Nope, I think I did write down the right number. Yep. I'm in a different order and I just didn't look closely. Sorry. 2.15. Okay, so 2.15 is our boiling point change. What's the normal boiling point of water? 100. So this change is going to be added because it's boiling point increase elevation. So it's 102.15 degrees C, which is our new boiling point. I like to make sure I write down my initial and then add it to show like, hey, I do know what colligative properties are, and I do know you have to add it. Copy. Okay, so then the last one is going to be delta T freezing point. Freezing point for this one, the molal freezing point constant for water is 1.86 degrees C per molal. I factor is still 1. Molality, still the same. So once you get that molality, write it down, circle it or something so you don't lose it, because you already worked hard. Multiply across, you get 7.796 degrees C. Okay? Yeah.
So the band number is in terms of the solute.
Solutes, yes. So the K number is in our constant for solvent, changes based on the boiling point or freezing point, the pressure constant, and the I factor is based on the solute. Yep. Because the bigger the I factor, the bigger the change. So it's proving to you that colligative properties are based on the number of things in solution, solutes in solution. Okay, so this is going to be what it's our original 0 minus freezing point, because it's a freezing point depression, 7.796 degrees C. So negative 7.8 degrees C. Which is nice, because most of the time North Carolina doesn't get that kind of negative temperatures. So our radiator fluid will never, never, never freeze, because we've got the ethylene glycol in it. Okay, so let's do one with molar mass. So I'm just doing 2 or 3 of these, okay? So solution of organic compound, we have 0.85 grams of this organic compound. Okay, we have 100 grams of benzene. Benzene's probably our what? Solvent, right? Has a freezing point of 5.16 degrees C. Determine the molar mass of the solute. What do you need to know? I don't have on the board right now. This is the new boiling point.
Okay.
You need K for what? For freezing K? K for whom? For whom? For benzene, the solvent, okay? So K for benzene, I think it was 5.12. Nope. Yep. Freezing point was just in the word. 5.12. Okay. So K for benzene is 5.12 degrees C per molal. What else do you need? Huh? Well, assuming it's organic, here it says it's organic, I'm assuming I is what? 1. There's one more thing we need, guys. Okay, we gotta calculate that. We'll get there. The temperature change, well, basically you need to know the original freezing point of benzene. This is the new freezing point of benzene, so you need the original to get the delta T. Yeah? Alright, so the original freezing point is 5.5 degrees C. That's not one you'd be expected to know. I'm just letting you know. Okay. Oh, I put 4.9. Darn it. Mine are going to be slightly off on yours, but we'll go with this. Alright, so we have formula delta T is equal to Kim. If we know that molality is something we still need to calculate, molality is just moles of solute over kilograms of solvent. Yes? So to get molar mass, what are the two things you need? Grams and moles, right? We have grams given to us. If we can isolate this information and get just the moles of solute, we can take grams divided by moles to get molar mass. Yeah. Because it says the solution has a freezing point, so I'm assuming it's after the solution from a pure solvent standpoint. Okay. So we need to get delta T, we need to get K, we got I. Find M, and then partition that out to kilograms and moles, and we'll get moles and we'll divide. Okay. So delta T for this is difference is 0.34. Is that right?
Yes.
Okay, I actually do have this right here. Okay, 0.34. K is 5.12 degrees C per molal. I is 1 because it's organic. And then I'm going to just put X over, because X is my moles, that's what I'm looking for, over my kilograms of solvent. How many kilograms of solvent? 0.1 kilograms of benzene. Good. Solve for X, you lovely calculator people. I need to recalculate X apparently because I used to different textbooks publish different things. So who knows where I got this constant from? You get 0.00664. 0.00664. Okay, so X is 0.00664. I know that looks itty bitty, but we'll make it work, right? So we need to do grams per mole to get the final touch of molar mass. So grams, I'm going to put molar mass over here, is 0.85 grams divided by moles got that we just calculated. 0.00664 moles. Molar mass is, I have to recalculate here. What is it? 128. 128. That's straight 128. No decimals here. Okay. Cool. All right. So this is a large organic compound. Weighs over 100. That's pretty large, right? A lot of our examples that we'll use today and later, you'll see biological samples. Biological samples are proteins, which are huge. Okay, like 7,000 grams per mole. Huge. 700. It's gonna be a lot larger. So if you get a number that big, don't be scared. You're fine. It's just a large macromolecule. All right, so like this is an example you can do later. That was I found in yours. NSMI, I can never say that. And there's a couple more in here that I think are really good. So like exercise 9 is freezing point, and that's a huge, huge, huge macromolecule. So I recommend that you use that for your benefit later, okay? So let's look at a phase diagram. Let's pinpoint how this phase diagram changes for based off the solvent initial to solution, and then we'll do osmotic pressure. Okay, so based on, I'm going to work with this. I don't know, you know, I have a big one on this page. I think I printed this for you. Maybe I didn't. Maybe I did. I don't know. Tell me, how do you think this is changing based on our colligative properties for solution? Like, you know that everything here represents what? It's the thing in between liquid and gas. Boiling, right? Everything here is boiling point. What happens to boiling point with the solution?
It elevates.
Right, it elevates. So am I moving this way or this way? This way as in right? Going right? Okay. So every point is shifting over. Okay? And then what happens to freezing point? They go which way? It goes to the left. Thank you for being more specific. And then this one has some wiggle room because the vapor pressure of this one's going to be different, but I'm going to go with this. Okay, so what's happened is we can now tell the original solution, original solvent, new boiling point for the solution. We can actually look here and get delta T. Because this drops down, the temperature is the x-axis, and this drops down to the other new temperature, so this can give you delta T. You can get delta T from a graph. I did print it? Okay, thank you. It's on the slides one. I was like, I knew I printed it for you guys. It's on the slides. Slides. So that will give you delta T boiling point. That will give you the elevation. And then the other one, this is your freezing point original. This is your freezing point after it's been depressed. And then that's going to give you delta T freezing point. So you can get information from a graph, basically. So when you're ready. Ready. Tara's always ready, guys.
Tara's always on top of it.
She's on top of things. Okay, so osmotic pressure is our last one, and then let you guys practice them, and we'll have some fun for other practice here. Okay, osmotic pressure. This is the fourth colligative property you did not learn about last year. Okay, your teacher may have mentioned it. It's like, hey, there's this other one we're not going to talk about. Because generally it's a biological example applied like in AP biology. So osmosis, remember biology? Osmosis is the flow of water from high to low concentrations. Yeah? The water moves up the xylem to go to the stuff at the top of a tree through capillary action. Okay? The xylem is vascular tissue of a plant. Okay. So osmotic pressure for this one is basically the pressure that needs to be applied to halt osmosis. Because there's a pressure differential like when the flow of water is occurring. So that's literally the pressure applied to halt osmosis. That's the definition of it. The flow of water is generally moving from high to low concentrations. A lot of times we do deal with the cellular process. We're talking about like hypotonic solutions and hypertonic solutions and isotonic solutions from biology. I do have a couple slides on that, but I'm going to tell you based off this YouTube. This is a YouTube. Okay, so we have a different in this sample. This is supposed to be water. Okay, this is water all through here. I just want to color it in. So there's water all through there, and there's a difference in solute level in each of these. So what it's showing you, this is after the process of osmosis has occurred, the water has flowed from left to right, which caused the water initial, they were the same, after they were different. So this difference here is the amount of water that flowed over to the right-hand side of this YouTube. And you remember how we can measure millimeters of mercury? Millimeters, like truly take a ruler up there and get millimeters of mercury. You can get millimeters of water, millimeters from gases. You can multiply density times height equals density times height. We could get the differences in the water. You can do that. We're not going to do that right now, but you could literally measure the millimeters of water, get millimeters of mercury, and say that's the pressure. Because it's just pressure. Yeah. No, it's a different pressure. This is pi, as in pi equals osmotic pressure. It does not have it's not a constant. It's 3.1, but it's not a constant. Okay, it's going to differ every single time you're in a new situation. So I like this one because I call this pi equals IMERT. Okay, IMERT. I is Van 't Hoff factor again. I. M. What do you think M stands for? Big M. Big M. Molarity. R. So R is equal to.
0.821.
Thank you. The pressure one, people. H1 atmosphere liters per mole. Okay, because we're dealing with atmospheric pressure, you got to use one of the atmospheres in it. The 8.31 is a joules one. That's what you use for energy. And then you can only assume T must be expressed in Kelvin. Okay. So those are going to be our constants that we need to, our variables that we need to know. Okay, so this osmotic pressure phenomena, it works really, really well with diluted samples because once you start putting too much solute in a sample, the pressures differ. So it works really well for dilute samples that, like, such as, let's see here, Tara and Sarah, you guys are going to be in the nursing class next year, yeah? Nursing classes, hopefully. I mean, I give you good recommendations. So. What do you put into a person who is lacking fluids? IV. What's the IV got in it? Saline. What's saline?
Water.
Salt water. What's the molarity?
Salty. Yeah, I agree.
What's the molarity of the salt solution? What's your interstitial fluid molarity? Nobody? Well, it's like 0.12 or 0.15 or something like that. Really, really, really dilute, okay? So this is truly a biological application. Because you need to know the molarity of the saline before you put it in somebody because you don't want to burst all their cells or shrivel all their cells up. The molarity of the saline solution should be isotonic to their cells so that you don't kill them. Right? Chemistry, people. Okay. So, this is obviously relates back to gases, yeah? Pressure gases. So I'm just going to show you how you can take the ideal gas law and convert it to IMERT. Basically, what happens when you take this one, put it over V? Molarity. That's all it is. Moles over volume is molarity. Okay? The pressure is over here by itself. I just changed pressure to pi because that's osmotic pressure, which says I'm talking about solutions, not gases. So all you do is divide by V. N over V turns into M. It's simply just the ideal gas law. Yeah.
So, for pi, are we putting that in our calculator? Like
No, you're usually calculating for osmotic pressure. I'm not going to call it pi. I'm not calling it pi. That is a symbol. I can put a happy face there. I don't care. I put a dinosaur there. It's literally it's not a constant. It's a variable you're calculating for. I'll put it as a happy face. Yeah. Huh? I'll do a dinosaur. Yeah. Okay. So let's do these two. Let's go ahead and let's do one together, and then we'll do the rest by ourselves. Because osmotic pressure is one that you've never experienced before, so I like to do more of this. Determine the molar mass of a certain protein. Protein, what are you going to assume? It's huge, right? Yeah. Proteins are huge, okay. The molar mass, you're going to anticipate it's very, very large. Okay. Determine the molar mass. 1.00 times 10 to the negative 3 grams, that's given, okay, of this protein was dissolved in enough water to make a 1 ml solution. Wow. Oh, 1 milliliter, guys. Okay, the osmotic pressure of the solution. So we're given dinosaur. We're given osmotic pressure to be 1.2 torr, temperature to be 25.0 degrees C. Calculate the molar mass of the protein. What do we not know? We don't know pi. I mean, we do know pi. I just like to agree with you.
I said I.
We don't know I. No, we do. We probably assume. We don't know moles, right? So we need to get molarity. Okay, so tell me how you want to do this. Ooh, I have a trick for you. Huh?
Do you do PV?
You use everything in.
Oh, you can't do that.
No use.
We can? Okay, I'm going to try it 2 ways. We'll do it your way first, and then we'll do it my way. Okay, so dinosaur equals IMERT. Okay, so I'm going to solve for x like Tara asked me to. 1.12 torr. Now, I want you to realize that we don't have R listed here, but it's there. What units do I need to have? atmospheres. We need to change this to atmospheres first, yeah? How would one do that? Okay, so 1 atmosphere over 760 torr. That's going to be dinosaur. And then I is 1. Sorry, assume 1 because it's a organic protein. Molarity is moles of solute, which you don't know, over liters of solution. 0.001. Okay, and then T. It's because I'm out of space. I just don't want to write it. No, I'll scooch. Oh no, don't scooch yourself. Okay, scooch over here. Okay, tell me about R. 0.0821 atmosphere liters per mole. Okay, and temperature. 298 Kelvin. Okay. Everything cancels except for moles. Okay. So X, which is moles, that's a terror question because I did not do it that way. So you guys help a brother out. Help a sister, brother. Yeah. Individual. I really wish I could ask you guys to do this in your head. I wish I could, but I would feel like a bad person. I would be a bad person. You would skip this question. How many moles did you get?
Small number.
Also known as what?
I got 1.79 times 10 to the negative 5. Did you get that?
I got 6.02 times 10 to the negative 8. I also just really was nonchalantly putting this in my calculator. Did anybody else get Abby? Abby, what'd you get? Say again.
I got 60.45.
Okay, here's what we did. 1.2 divided by 760 divided by 0.0821 and the product of that in 298. Yeah? And then multiplied by 0.001.
I get 6.023 times 10 to the negative.
Thank you. Woo! Nonchalantly putting in the calculator works. Okay, so that's our molage. Oh, well, you did it wrong. That's what happened. Grams per mole. Hey, I'm just doing it the way Tara said. I'm going to show you guys another way in a second. I like Tara. Tara, you're good people, but I'm going to show you another way too. What is moles? 1.00 times, grams. Negative 3 grams over that number. 6.02 times 10 to the negative 8 moles. Now, calculadora. They can come if they have a key.
I hear them rattling there too.
1 times 1.00 times 10 to the negative 3rd. Divided by that number. What'd you get? Woo, doggies! 16,601 grams per mole. Crazy high. What's to be expected for a protein? Yeah? Okay. All right, I'm going to show you another way, and I have to write on here because Allison's not here, so I have to write on here. All right, so that's big and bad. I'm going to show you another way. Now, the answer is not going to be, no, it will be really, really similar because it's the right answer. Yeah. Okay, so how did we find molar mass in gases?
So is this the wrong answer?
This is correct. This is correct. Sorry, I was thinking about another problem, but we skipped
Molar
it.
mass was dirt.
Dirt. Say again. Dirt over P. Do we know dirt?
Yeah.
Yeah, we know density. Density has to be expressed in what for gases?
Grams per billion.
Grams per liter. So grams, liters, R, T, P is dinosaur. Okay?
That's better.
I like this better. It really didn't take us much at all. We did it. We saw for moles. But I like this better because we can plug in numbers and no division, nothing crazy like switcheroo. You just do that, divide by that, and we're done. You get the same thing. You get 16,600 grams per mole. Okay, cool. You get this. You get that. Okay. Now, nursey people. What concentration of sodium chloride in water needs to to produce an aqueous solution isotonic with blood? Common law knowledge, people. I know. I told you I asked my husband that. I said tetra should be common knowledge, and he said no. It's the answer on here. But let's do this real fast. Go, go, go. What am I doing? What am I doing? What am I solving for? Solving for molarity. Dinosaur equals I mert. Divide by I ert. Okay, so molarity is 7.7 atmospheres. What's that sound?
The whistle.
2?
Dog
Yeah.
whistle sound.
0.0821 atmosphere liters per mole. Okay, and 298 Kelvin. Okay,
What is all the dots?
atmosphere liters per mole K.
So do you want us to use the theoretical I or the actual I?
Use the theoretical I.
Okay.
Whoever is making a noise, I'm going to shove it in your mouth. 0.5157 molar. That's your saline isotonic solution to our cells, so your little cells don't burst. Yay, science. Okay. Now, I already did this. I already did that. Oh, no, well, I will make sure that you have this definition of some sort down. Osmotic pressure is the minimum pressure required to stop osmosis. Minimum pressure. Cool. There's just always an external pressure on you, atmospheric pressure, so you have to kind of counteract that. This is just definitions. You can read your NCS in that. Okay, reverse osmosis. This is an application of osmotic pressure. This is used for desalination.
My water is done by reverse osmosis.
It's a very heavily polluted industry. It pollutes the waters, but it makes the water pure for drinking purposes. So desalination just means take the saline or salt out of water. They have a lot of these plants on the coast, obviously, because you have a lot of salt water accessible. A lot of them in France, because France is all about that bottled water, making sure it's real desalinated. But there's a lot of thermal pollution put back out into the waters due to the immense amount of energy that's required to reverse this natural process. So it's a high thermal pollutant industry, not necessarily like chemicals and stuff, but basically if you increase the thermal pollution, what are you doing? And basically that means you're putting hot water back in a cold water source. What are you doing to the gases in the water? Heating them up, and then they right. So you're increasing the temperature of the water, so the gases evaporate out. Well, what gas do you think is important to have in water?
Water? Oxygen?
No. Say again.
Oxygen.
Dissolved oxygen, right? You need dissolved oxygen in the water. So if you decrease the amount of dissolved oxygen, you're decreasing the flow of dissolved oxygen through like little fish gills. There's no diffusion of the oxygen through the fish gills, so the fish, there are large amounts of fish kills, they die, amongst other things, like, enzymes don't function appropriately because they have to function at a specific pH and different temperatures. So there's a lot of domino effects after that. But hey, we get some clean water, people. Reverse the flow through a semi-permeable membrane. I'm not going over semi-permeable membranes. It's pretty self-explanatory. Okay, but more applications. Dialysis. Yeah, dialysis. Kidneys. Kidneys naturally will filter out different solutes from water, and you pee out the water, you keep some of the solutes. Some of the solutes are waste. But you do need to keep, like for example, your red blood cells. They're on the one cycle that comes back to the body. That would be really bad if you started to pee blood. Bad story. Okay, so you have to have a semi-permeable membrane between your kidneys and wherever the filtrates go. I used to remember that. Your readers, something like that. So for dialysis, basically they hook you up to a machine that artificially does that, but the membrane has to be able to select what goes in, what goes out. So they keep the dialysis membrane in a specific spot, and it's like a weird tube they have to put in there. And then they'll keep the red blood cells in one location, and they'll have the solutes or water, solutes and water that can come through another location. So there's a lot of applications of osmosis, and they also have to keep it at a certain pressure, osmotic pressure, so you don't lose all your blood, like the kid that I was next to at the blood drive. So, He bled all over the gym floor.
Wow.
Wait, who was
Because he passed out and the whole thing fell out of his arms. I don't know.
Who was
I would turn away. I
I
don't know. I really don't know. I just turned away. I was like, I can't deal with this. Then my heart rate went up, and I was like, I don't know if I can get blood right now. So I'm a wuss. Okay, so dialysis tubing differs in osmotic membranes because they allow for diffusion of particles. Osmosis means only water, right? And then this is going to be our discussion of hypo, hyper, and iso. And I have it on the next slide for you. So solutes generally move with this concentration gradient. They move from high to low concentration. They don't build up against the concentration gradient. So this is the application. I'm skipping this picture because I have it right here. Oh, this is just a quick hello. Are you here for dialysis too? No, I work here. He's a stir bar. He's stirring iodine solution or something. Maybe it's urine.
The thingy.
This guy?
Yeah.
You guys don't remember doing the baggie lab in biology?
Yes, we did it.
Biology bag. Starch in the bag. Iodine in the outside solution. Semi-permeable membrane. Iodine goes through. Starch doesn't come out.
Yeah.
Baggie, starch, iodine.
I understand.
Stir bar.
I didn't.
Okay, bye. Bye, girl, bye. Okay. So, isosceles triangle. Same, yeah? Same sides? Isotonic, isosceles triangle? Don't tell me.
It has two same types.
Yeah, but I'm just saying iso means same. That's what I'm saying.
Oh.
Same. Iso just means same. Isotonic solution means you have the same concentration, same osmotic pressure pushing both directions, no net change. Hypertonic, this is how I teach biology. Hypertonic people are really, really hyper. And like I think of my little brother, and he's like his toothpick. So he pushes all the water out of him because he's really hyper, and he loses all his water. So he shrinks. Normal red blood cell shrinks, small. It's called crenation. Crenate. Crenate? Yeah. Cremation. Crenation. This is a red blood cell, by the way. Crenation is a word you use only for red blood cells. Crenation means that the cells shrivel and shrink away. Basically, the water is leaving the solution, so the osmotic pressure is kind of pushing it out. Okay, the osmotic pressure of that inside solution, because you realize red blood cells are bathed in like isotonic or bathed in some sort of fluid, but the solution inside is hypertonic to the solution outside, so the water is pushed out. Okay, opposite for hypotonic, hippo. Okay, hippos are large. They are large creatures. Large, swell. So hypotonic solutions, the movement of particles of water come inside. So we have a swelling. Does that have a word? Lysis? Hemolytic? Hemolytic solution. So crenation is shrinkage and swelling. And getting smaller, and then swelling is as hemolytic. It tends to burst. Because basically this gets so big it starts to burst. It's like exploding. Yeah? Looks like exploding? Beautiful. Okay. So it's exploding because it's getting too large for the cell membrane that's holding it. Plant cells don't burst because they have a what?
Cell wall.
Cell wall. Go science. Good. Okay, so this is what this picture is denoting as well. Alright, so we're almost done here. Done. Okay. Okay, so I first want to make sure you're good to your lab tomorrow. So this I'm going to narrow down because I have this page printed for you from my old textbooks. I really, really liked these questions. I latch on to questions and I don't let go. What's my answer? Let me pick out the ones I want you to do right now. But you have two options for your free time right now. You are going to either finish your now later, you're good and dandy with the simulation, or go back to the back and start the simulation, which I didn't put up here because I didn't really know. But after that, we'll talk about Google Docs answers. Okay, so take 15 minutes of your own, 20 minutes right now, and they'll talk about Google Docs. Yeah.
I'm stretching.
Okay. The pre-lab can be on your Google Doc, right? This, that's what I'm going to
that
tell you.
is the
Yeah.
sheet? Okay.
This is the sheet I'm talking about from right here, but I'm going to pick out very few of these to do, okay? I want you to for sure do your now and later and your pre-lab stuff if you do not yet.
Okay, so for the pre-lab, did you want us to do part 1 and part 2? Because I was okay.
Because part 1 was just video,
Yeah.
part 2 was do the simulation.
Okay, and then do you want it on the Google Doc?
It'll be all submitted with your procedures. So
Okay, because I didn't know what you wanted. Because like for part 1, you wanted us to do drawings, but then like.
oh yeah, I forgot I said drawings. You can put that in your lab notebook. That's fine. I was just trying to keep it cumulative for you.
Okay.
That's all. I was just trying to help. Yeah. You're not stretching?
I was confirming that we were supposed to answer these questions like on the actual
On the simul,
You're like trying to block.
on the lab sheet.
There were questions for that.
The pre-lab, I said to only do the part 1 and 2 that I posted, but if you did those will be embedded in your pre-lab, because those are the consortium, the Concord consortium, because you guys already know a lot about IMFs. Basically, I was just trying to get you to quickly recap and then move on. But if you did them,
I like the simulations focus more on this as the actual questions in pre-lab.
the actual questions in the pre-lab, I can't actually remember what they are, so I have to look.
This is